Alrighty ho, my name is Max Joyce with Physics 2211, lab number 1, constant velocity. Alright, quick overview. We're going to do an introduction. We're going to talk about rolling a tennis ball. We're going to talk about some computational models and a tracker. We're going to wrap it up with some graphical analysis and some conclusions. Alright, quick introduction. We got two big things at play, constant velocity. And what does constant velocity mean? It means that we're utilizing Newton's law of inertia. We'll get into both of those things later. Talk about two equations real quick. Newton's second law and position update formula. We'll get into those in just a moment. Constant velocity and inertia, objects love moving. That's Newton's first law, essentially. An object will stay in motion unless acted upon by another force. Now, what are these forces? They're interactions, and we know that interactions cause a change in velocity. So what is interaction? Like I just said, it's a force. These forces can be force of gravity, force of an electric field, force of applied, force of friction, all these different types of things. So how does a net force affect velocity quantitatively? Because that's what we want to know. So, and we use Newton's second law for that. Relates net force or interaction to a change in momentum over some time period. That's what delta P, or change in momentum, means. Delta T, of course, is our change in time, and that's going to be equal to our sum of our net forces on the system. All right, and then after doing a little bit of algebra, we can figure out that the final velocity is dependent on the net force and the amount of time the net force is acting on the system. Of course, we can look at that bottom equation right there and say that V sub F, or our final velocity, is equal to F net delta T over our mass M plus our initial velocity. Pretty straightforward. All right, now we're going to go into our actual experiment that we did, which was rolling a tennis ball. So this tennis ball was rolled to the right in a straight horizontal path, and when we're analyzing this little video right here, we can tell that our system is in fact the tennis ball, and our surroundings is the Earth. But what else? Our surroundings is going to be the Earth, the table, and of course the hand that pushes the tennis ball. All right, so we're going to talk about force diagrams really quickly. Force diagrams, of course, help with visualizing forces. As you can see, the white circle is going to be our system, the tennis ball. The red circle is going to be our center of mass, and we can see the force vectors coming off of that. So we got four forces. We got the applied force, we got the kinetic friction force from the table, we got the gravitational force, and then of course we got the contact force of the table, that normal force. So friction applied force will be ignored during this because they'll change our velocity. They're going to cause a interaction and make it so our velocity in the x direction is not constant, and that's what we do not want. All right, moving on to our tracker model. Essentially, what we got right here is a short video showing the tracker itself at work. So essentially, this is taking our x position at every single frame and putting it into a table, and that table is then getting converted into a graph. All right, as you can see, the table is tracking our time, our x position, our y position, but we're only looking at the time and the x position for this. We can see that graph looks like a linear relationship, and that's what we want to see. Constant velocity, of course, there's going to be a linear relationship on that position versus time graph. Okay, next thing I'm going to do is talk a little bit about our computational model that we use. So there's a few things we need to figure out before actually using that model. First off, we need to know the initial velocity of the ball. Now, the initial velocity of the ball is super easy to find out. All you have to do is just put it in the tracker, and it shot out 0.343 meters per second. Next, we had to find the time step, which was going to be 0.033 seconds. I found that just by looking at the table. Pretty self-explanatory. Next, we had to figure out what vector was going to be added to our velocity vector each time step. And what vector was going to be added to our position vector after each time step. And I figured that out just by simply multiplying the velocity that we're given of 0.34 meters per second times that time step of 0.033 seconds, and that gave me that vector that I was going to add to the position every single time step within our loop. All right, talking a little bit about the graphical analysis. As you can see, tracker versus the computer model. The tracker's in blue, computer model's in green. Of course, that computer model is perfectly linear. Our tracker is not, because I am not a robot. I cannot perfectly put that little thing, that little dot, inside the tennis ball every single time. So that's a little bit of error on my part. However, we do see a general trend of a linear relationship between the two. Now, my tracker wasn't perfect, as I said earlier, but it's pretty close. Pretty cool analysis that we can pull that both of them are in fact that linear relationship, and that's what we want to see, because we have a linear relationship between our x position and our time when velocity is constant. All right, so talking about these additional questions a little bit. So what if we moved our essentially our reference frame in our tracker? Now that would change things up a lot essentially. So instead of starting at 0 essentially when we're looking at the graph, we'll start below the x-axis in the negative x direction, and then we just increase as we moved up. So if our reference frame was all the way to the right, we would end essentially at x or on our x-axis, which would be our position equals to 0. So what does that mean question, really, I've already talked about it. Is it possible for you to say how many pushes and pulls are added together to give 0 net force in this case that we observed? Yes, it's going to be our gravitational force and that contact force that we saw with the table. All right. Thank you all for listening.